Okay, students, let us continue the discussion. So we know that glucose is a polyhydroxyaldehyde or ketone. But how did we come up to this structure? There are certain experimental evidences which confirm the given structure of glucose. So I'm not discussing the write-up, I'm just discussing the equations. So when glucose is first heated with hydrogen iodide, it produces normal hexane. Now this experiment proves that all the 6 carbon in glucose, they are arranged in a straight chain. There are no branches. Second experiment is treating glucose with hydroxylamine. You know that we have been telling that glucose is having aldehyde group. But what is the evidence that glucose is having aldehyde group? Now you have learned the reactions of aldehyde and ketones, and you know that carbonyl groups, they undergo nucleophilic addition reaction as well as they react with derivatives of ammonia. So here it is a reaction with derivative of ammonia, and we all know carbonyl compounds, that is aldehydes and ketones, they react with hydroxylamine to form a class of compound called oxime. So glucose is also found to form oxime, which confirms that it is having a carbonyl group. But remember, till now we do not know whether the carbonyl group is aldehyde group or ketonic group. The next experimental evidence is reaction with hydrogen cyanide. This is also nucleophilic addition reaction, and if you remember in aldehyde when we knew that hydrogen cyanide adds to carbonyl groups to form a class of compound called cyanohydrine. Glucose is also forming cyanohydrine when treated with HCl. So this experiment also confirms the presence of carbonyl group. Now the question arises, how do I know whether this carbonyl group is aldehyde group or ketonic group? Because you know that since glucose is a monosaccharide, it will reduce tolerance to agent and fell in solution irrespective of whether it is having aldehyde group or ketonic group. So we cannot make use of that experimental evidences. So we go for another test, that is using another mild oxidizing agent, and that is bromine water. Bromine water is a mild oxidizing agent. So what it will do, if there is aldehyde group, it will oxidize the aldehyde group to carboxylic acid. So it has been found that glucose, when treated with bromine water, forms gluconic acid. You can see there is a COOH group formed. This confirms the presence of the carbonyl group to be aldehyde group. Another experimental evidence, by choosing a strong oxidizing agent, that is nitric acid, glucose forms saccharic acid. What is saccharic acid? Saccharic acid means you have two COOH group in the two terminals, and in between you have CHOH 4 times. So formation of saccharic acid confirms presence of a primary alcohol group here. And it is also found that when gluconic acid is oxidized by nitric acid, it also forms saccharic acid. So this confirms the presence of a primary alcoholic group. The next reaction is with acetic anhydride. When glucose is treated with acetic anhydride, it forms glucose pentaacetate. And you know acetates are esters. So we are saying that glucose is having many OH group. So how many OH groups are there? Since pentaacetate is forming, which means there are 5 ester groups formed, that means glucose is having 5 OH groups. So combining all this information, when we draw the structure of glucose, we find this is the structure of glucose. If you remember, we have discussed the structure in the class also. We draw glucose structure in the vertical manner. You have 1, 2, 3, 4, 5, and 6 carbons in the vertical chain. Then if you remember, we have put here plus, 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 minus, plus. The meaning of plus and minus means whenever I am writing plus, OH should be placed on the right hand side, and minus means OH should be written on the left hand side. So when we write OH on the left hand side, make sure you don't write OH. The oxygen should be linked to carbon. Now you can see there are 4 chiral carbons here. 1, 2, 3, 4. There are 4 chiral carbons, as each carbon is attached to 4 different groups. So here we have 1 carbon which is not chiral because it is having 2 hydrogens attached to it. This is the primary alcoholic group. In the topmost position we have the aldehyde group, which is also not an carbonyl carbon. Rest all of them, they are carbonyl carbons. So it is expected to show optical activity by combining all the effects of all the carbonyl groups. So name of this compound is D plus glucose. Now why this D? The configuration D means, you see, by convention a molecule is assigned D configuration if the OH group attached to the carbon adjacent to the primary alcohol group is on the right hand side, irrespective of the position of other OH groups. So here you may notice that this OH and this OH, this is the referral molecule, this is called D-glyceraldehyde. So here this is the primary alcoholic group, here we have the primary alcoholic group. As OH on the first carbon is on the right, this is assigned capital D. Okay, what is the position of the OH in the rest of the carbon? We are not interested in that, but we are interested only in the position of the OH on the first chiral carbon from bottom. So that's how the name of the compound becomes D plus glucose. But fortunately or unfortunately, this structure is found not to be 100% correct because of some more of the experimental evidences. And these evidences compel people to think that glucose exists as a cyclic structure. You see the points? The open chain structure of glucose could explain most of its properties but fail to explain certain properties. Number 1, despite having the aldehyde group, glucose doesn't restore the pink color of Schiff's reagent. You know, Schiff's reagent is a kind of reagent which helps you to identify the presence of aldehyde and ketone group, just like Fallin solution and Tollens reagent. So here we find that glucose is not capable of producing pink color with Schiff reagent, though it is having an aldehyde group. Second evidence is it doesn't form a 2,4-DNP intermediate. Remember how we have discussed that aldehydes and ketones, how do you identify? In the lab also you have to do by adding 2,4-dinitrophenylhydrazine. So if the compound forms a yellow precipitate with 2,4-DNP, then you confirm that it contains carbonyl group. But glucose, we know it has carbonyl group, but it doesn't react with 2,4-DNP, and it also doesn't react with sodium hydrogen sulfide and ammonia. So these are some of the experimental evidences which doesn't tally with the open chain structure of glucose. Next is glucose pentaacetate doesn't react with hydroxylamine. So if glucose is having aldehyde group free, then it should react with hydroxylamine whether it is in the pentaacetate form or not. But once it forms the pentaacetate, it doesn't react with hydroxylamine anymore. Though with free glucose, it does react. The third experiment is very important. When glucose was crystallized from please remember these conditions, okay? Concentrated ethanolic solution at 303 Kelvin, it gives a solid form of glucose that is called alpha form. Okay, and it has a melting point 419 Kelvin and a specific rotation, that means optical rotation of plus 111 degree. On the other hand, if you do the same process by changing the solvent, now from alcohol you change the solvent to pyridine and you change the temperature in which you are doing the crystallization process. Earlier we did at 303, now they are doing it at 371 Kelvin. Then we find the glucose crystals which we get, it has a melting point 423 Kelvin. Earlier it was 419 Kelvin. Now, if a compound is pure, it cannot have two different kinds of melting point. Okay, so the other form is termed as beta form. Now, the alpha form and beta form, if you remember, we have discussed in the class. How to draw it, that also we have discussed in the class. So here we have the Fisher projection formula, how the OH from the carbon 5 is combining with the aldehyde group in carbon 1 and forming a OH group either on the right in the alpha form or on the left in the beta form, and how we convert them to Howard structure. All these are discussed in the class. So hopefully you can correlate. So with this we come to the end of the structure of glucose, and the structure of fructose also we have done in the class. You know that fructose is a ketohexose, meaning it has a ketonic group and it has 6 carbon. And here also the sequence of OH we put is plus 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 minus plus. And here, unlike glucose, we have two primary alcoholic groups, 5 OH groups only, but out of 5, 2 are primary alcohol. In glucose, we have only one primary alcoholic group, and in carbon 2, we have the ketonic group, and in glucose, in carbon 1, we have the aldehyde group. Okay, so glucose and fructose. For fructose, how the structure has been derived is not included. You have to only know the 5-membered ring structure of fructose and what we mean by anomeric carbon. So with this, we close this video today, and the next class will have disaccharides.